So we've already said that for a cycle in a PV diagram, you can actually have conserved entropy. So the entropy located at any position is the same. So if you cycle around, you come back to the same entropy. And those cycles can be made out of a variety of different isothermal processes that we've already talked about. So this is just a summary to show you that you can calculate the change in entropy for all these different processes. The first one is isotherm, which has a constant temperature. We've already said that we can write pressure as a function of volume, which is nRT, again that's a constant, over the volume. Using that, we were able to calculate that the change in work is equal to nRT times the natural log of the ratio of the two volumes. And since it's at a constant temperature, then there is no change in the internal energy. That implies that the heat transferred is equal to the work, and that means that the heat transferred over temperature is constant in this case, so we don't need to bother with that integral. We can just see that the change in the entropy is equal to nR, natural log of the ratio of the volumes. And so let's double check our units for this. Remember that the entropy units are joules per Kelvin. And if we see that the only units in this problem come from the number of moles and this ideal gas constant R, and we can see at the end of the day N times R, it does actually have the correct units of joules per Kelvin. We can do the same thing with an isobaric process. Again, this is a process where the pressure doesn't change. Here we can see that the work done is that constant pressure times the change in volume. And we've already shown in the last lecture that the heat that's absorbed by this system is equal to 5/2 nR delta T. Using the same type of equation that we had before, where delta S is equal to C times the natural log of the ratio of the temperatures. Remember that the heat capacity for an ideal gas undergoing an isobaric process is 5/2 nR. And again, we can see that the units work for this as far as the change in entropy is concerned. We can also do an isochoric process. Again, the work done is 0. The change in the heat for this system is the heat capacity, which is 3/2 nR times delta T. And again, if we use that in our equation for delta S, we see that the change in entropy for this system, for this type of process, is 3/2 nR times the natural log of the ratio of the temperatures. We've already discussed the adiabatic process. This is a process where no heat is transferred, and that implies that the change in entropy is 0 for this process. And we've already talked about that the total internal energy is all changed completely by work, and you can actually calculate all of these different things. So again, these last slides are kind of summary slides to help you put it all together in one place and think about these things all together in combination with the slides from the last set of slides, movie slides from last lecture. And again, we can talk about the cycle. This is what I said earlier, it's just that all of these variables that you're seeing, including temperature, pressure, volume, total internal energy, they're all state variables that describe whatever location you're at on this PV diagram. And of course, S is also one of these state variables, which means that the entropy change for a cycle is 0. And these systems are the basis for engines, heat pumps, and refrigerators. Of course, anything that's perfect on this PV diagram cannot really be fully actualized in real life, although we can come up with a variety of different idealized motors.